Hi everyone, my name is Deven Patel. I'm from Université Laval. I'm working on a how-to-balloon project that's called the high contrast imaging balloon system. In very simple terms, what this basically is taking a telescope, putting it into an altitude balloon, and setting it up to about 35 to 40 kilometers altitude to take some really cool pictures. And these really cool pictures are high contrast images. So before I get into the presentation, to the project itself rather, I want to talk a little bit about what high contrast imaging is. And this is not working. That's alright, I'll just do this. There you go. So, in the context of our project at astronomy, at least, high contrast imaging is basically being able to a technique that's used to detect the light of faint objects when it's orbiting a parent star, something that's a lot brighter than those exoplanets, those faint objects. So, as you can see here, this is the image of an HR 8799 star. It has 4 exoplanets, and the way it was seen by Sam Wallach, the Aberration Institute of Astrophysics, was using a coronagraph and allowing those exoplanets, the light from those exoplanets to reach the detector of the camera. And this was taken at the Mech Observatory in Hawaii from 2009 to 2016, so it's a string of images giving you this animation here. And this is basically what HiCIBaS is trying to do. They've now span 7 years, but in the span of about 4 hours overnight on a one-night mission. And so HiCIBaS is really the first project of its kind with our group and our university, so we're really trying to develop that framework for the first project of its kind. And that basically means that we need to have a lot of struggle to make sure that we have the systems that we need, the components that we need that are ready for future missions, for future high contrast imaging missions. So to do this, we have some objectives that we have for ourselves that we want to move over to the next iteration of the project. The first is to study and gather the data on wavefront errors and instabilities. Basically, what we're trying to do here is characterize the atmosphere at 40 kilometers. Now, this is invaluable data not just for ourselves for future missions, but also for all future optical payloads, because we really want to see what kind of aberrations we can experience at that altitude. And using this information, we can better tailor our systems to deal with them in the future. We also want to develop and test a new type of the low-order wavefront sensor. I'll talk a little bit more about what that is a little bit later, because I don't expect everyone here to be physics major. But basically what that it's going to be able to do is help us measure those aberrations. The third thing we want to do is develop and test a sub-milli-arcsecond precision pointing system. This is one of the biggest challenges we have for that high altitude, because we're going to be operating it remotely and preferably automatically. And the last things we want to do is basically validate the performance and operation of some components, key components in our systems, namely the deformable mirror, the coronagraph, and the Nüvü EMCCD cameras. We are happy to say we're launching under the STRATOS program. I know a couple of you guys here. We're launching from Timmins, Ontario, by the way. That's part of the August 2018 campaign. And I saw a couple of you guys in here yesterday. Pulled your cameras to Google where Timmins, Ontario was. So if you guys look like you guys were looking slick, I saw you guys. So that's a view of Timmins, the Timmins base on the left side there. Hopefully it'll look like that when we go in August. But that is where our launch campaign is going to be happening from. I'm not going to talk too much about this because Steve did go over it in his presentation yesterday to do a lot of overlap. This is the trajectories that we experienced yesterday, that we plan on seeing for our own balloon. It's really dependent on the day-to-day basis, on the weather conditions and the jet streams. We do expect a maximum landing distance of 500 kilometers. Thankfully for us, we're not the ones recovering, so that's not our problem. This is a look at our flight profile. As you can see, we're launching from 11:30 p.m. at night. We're about to hit our sitting about 2 p.m., which gives us about 4 hours to do whatever we want in terms of imaging and data collection. We're trying to work on ways that we can optimize that time that we're imaging and taking data by minimizing the time we have to do for diagnostics and calibration by doing it during ascent and between target stars. Speaking of those target stars, these are the target stars. I think it's a little too small for you guys to see, but I'll take from left to right. It's Altair, Vega, Capella, this Betelgeuse, and Rigel. Those are the 5 stars that we're going to be targeting throughout the night. They were chosen based on relative intensity, how bright they are relative to other stars in the sky, and also the effort it takes to follow these stars. Yeah, that's basically what it was. And also all the time that they're visible from, because some of these stars appear earlier in the night, some of them appear later, some of them disappear sooner than later. So that's all considered to be made in the choosing of these stars. So this is a description table from Stellarium. If you guys haven't seen that, if you guys are into astronomy, I highly recommend you guys check out Stellarium. This is a simplified view of our project. So we have two main scopes, the star camera and the telescope. The star camera is going to be used basically for our pointing system, for our guiding of the telescope. The telescope itself obviously is collecting the starlights. It's the light from that is being directed to the tilt mirror, and that light is being sent into two different optics systems. The low order wavefront sensor and the deformable mirror. You'll see that the deformable mirror also has a wavefront sensor. I'll talk a little bit more about that a little bit later in the presentation. That's exhausting, I know. But what you need to know about this slide is basically we have a pointing system up here and the optics system down here. And what's really important to note is this little loop right here, this little feedback. Because our pointing system, as good as it is going to be, we're not going to be able to get that ultra fine precision that we want. So we're going to rely on our optics system to give us that extra bit of precision, that sub-milli-arcsecond precision that we want. So our pointing system starts with the kinetic gondola. If you guys were here yesterday, Steve talked a lot about kinetics and how they're providing the gondola and the balloon for these missions for the next I don't know, decade or something. And it's the same for us. So we're using the carbon 2 pointing gondola. It's able to give us a pointing accuracy of about 3 degrees, which, to give you guys perspective, it's 10,800 arcseconds. Now we're trying to go for sub-milli-arcsecond precision, so obviously in the azimuth direction, this isn't going to be enough for us. So we have to have our own pointing system to boot. So this is a look at our design of our map for our telescope at the moment. It's still being developed, still being worked on, still a lot of work to do. But what's important to note here is on the left side you'll have you see the picture of the bottom motor, the bottom rotary platform. That's going to be giving us that fine correction in the azimuth direction. And on the right we have two motors, one for the telescope itself and one for a mirror behind that telescope. That's going to give us the accuracy that we need in the elevation direction. In the gondola, we have 40 degrees of freedom for a telescope in the azimuth direction, negative 20 to the left and 20 to the right. And in the elevation, we also have 80 degrees of freedom, 20 below the 0 and 60 above. So again, this is another exhausting looking slide, I understand. But what's important to note again here is that the first part of this program basically is what's needed for our pointing system to operate. So the first three things we need are one, the coordinates of the star, two, our position in the sky relative to that star, and three, the boresight error. And the boresight error is basically the error between our scope, our sky tracker scope, and our telescope, because there is an inherent flaw there, and we need to make sure we countermeasure that error. But once that program is started, we'll be able to get about 10 arcseconds of error in our system, in our pointing system. And we achieve 1 to 2 arcseconds on our third loop right there. And as I said, the rest of our pointing accuracy is coming from our optics system. So this is our optics system in our gondola. It's just the bare trajectories of our light rays. There's no structure that's there, but what's important to note here is a part of the circle in red that's considered our back-end optics, and that's all static. And this is a design choice that was made for two reasons. The first, it just reduces the complexity of our system, and this is so important because we're in a high-risk mission with a bunch of new people to this application, to the space industry, and all this kind of stuff. And not all of us have that experience, so we need to minimize and mitigate those risks as much as possible. But for the second reason, more important reason rather, is actually the kind of vibrations that come from moving components and rotating components. Those mechanical vibrations can affect our pointing system and the accuracy that we have, and it causes a jitter in our line of sight, which is also a limiting factor in when performing any kind of imaging in astronomy. This is an intuitive look at our optics system. So from the left, we have that telescope. Actually, I have a little animation here. There it is. So we have the light coming from the telescope into the tertiary mirror. The tertiary mirror literally its only job is to point that light ray as down vertical as possible. At that point, we get to the first port, which is the boresight camera. That's going to give us that boresight error that I was talking about earlier. And then we get to our TTM, or tip tilt mirror, which is going to give us that fine steering, or that fine precision that we want in our pointing system. Then it's the right redirection to the ports 2 and 3, which is the lower wavefront sensor, and the deformable mirror, which I'll talk about shortly. And the fourth one is calibration sources that we have. So we're going to have a calibration source basically using, basically giving us visible light that we can, visible and infrared light that we can use for our two optic systems. So in a worst case scenario, for whatever reason, if we can't see anything, if we can't detect any light, we can use those calibration sources to at least validate the performance and the operation of our optic systems. No, sorry. Like I said, I don't expect everyone here to be a physics major or an optics specialist and like that, so I just wanted to talk a little bit about aberrations really quickly. So aberrations is basically what something that you can't really avoid with real lenses. So in a perfect scenario, all the rays of the light coming from an object pass through this lens and focalize on a single point. Like I said, in a real world application, it doesn't really happen. Rays of light tend to bend and they focalize at points a little bit before that focal point, causing a little bit of a blur, a little error in our images. And that's basically what we want to see with our lower order wavefront sensors. So the purpose of the lower wavefront sensor is literally to transform that that wavefront error onto a light intensity distribution map. And using this, we can be able to correct for that little bit of error, send it back to the tip tilt mirror, giving us that correction that we need, that sub-milli-arcsecond precision. The other part of the optic system is our adaptive optics, our deformable mirror. So how that basically works is the light comes from the telescope, hits that mirror, and that light is split into two different portions. We have the portion going to the high-resolution camera, which is the imaging part of it, and the wavefront sensor. This is what measures those wavefront aberrations, those errors, and that's able to tell the mirror how to change shape in order to correct those aberrations, so we can get a high-quality image. What's really important to note is that those two systems, those two components rather, in the context of our project, is one component, is one camera, and reducing the amount of components and complexity, again, like in our system, is again reducing risks, and it's so important for future missions because we want to be able to have as minimum components as necessary for our project. This is a look at what we would see from that kind of data. So on the left we have a pupil plane phase, so that's the phaser a pattern of the phaser that we would see that would be sent back to the deformable mirror to make those corrections. And in the middle we have the focal plane PSF that we can see on the detector. And on the right side is just a zoomed in view of that focal plane PSF. So like I said, this is one of the components we wanted to validate in the house environment. It's a Nüvü camera. So this is a couple of images that I wanted to show you guys just because I thought they were really cool and I wanted to show it to you. On the left side is an image of the NGC, I think 7731 galaxy, I believe. And in the middle there we have a radial map velocity of it. And it was made using an IFS, an integral field spectrograph, with a Nüvü camera. Just to give you guys an idea of the performance of these cameras. We will be doing our communication through the PASS module, the CSA, since we are flying with them. But what's really cool about our project is that we're going to have an SQL server that is going to allow us to send packets of information periodically through that module down to ground for us via the downlink that they've set up. What's also really cool is that we'll be able to, by the touch of a button, be able to request packets of information as well from that SQL server for whatever we want in terms of temperature of our cameras, the detector temperatures, all these kind of things we want to use for diagnostics to measure performance of those components as well. And to give you guys a timeline, so we have a big deadline, not big deadline, but a big milestone coming up in November, where we're going to be testing our low-order wavefront sensor at the Mech Observatory. After that, well, basically from here until December, we're going to be finalizing design and developing those ideas further. In January, we have our FDR, our final design review, and from then until about May, probably June though, to be honest, we're going to be working on the assembly and testing of those systems and components. And from there, we go to Timmins a few weeks in advance, prepare, and then we launch in August of 2018. Obviously, this isn't a solo effort. We have a great team behind me and everyone else, all the collaborators as well. The team right here is Denis. He's a research scientist at Université Laval. He's working on the optics side of things, giving support to those master students. Nüvü Cameras is working on the pointing system. Simon is our project manager. Me, I'm working on the mechanical aspect of the project. Guillaume is the low-order wavefront sensor specialist. Mireille is working on the deformable mirror, the adaptive optics. And Cedric is working on the communications and data management. And again, just thank you to all our collaborators. We haven't gone as far as we have without them, and I thank you for the community support. Thank you.